Hi, good morning, and welcome to the ZP Developer Zone webinar. So I'm actually recording this because I did do it live, but unfortunately the live version I didn't have enough bandwidth, so let me jump into it. So today's the 18th of April 2024. All the questions today are around the potassium sensor. Any links that pop up, I'll make sure I put the links underneath the video as well. The first question is, somebody's using two different solutions. They're getting response to potassium, but there's an offset difference between the two solutions, and I will address that today. Because I think the way they're testing the sensor by bringing solutions on and off, it's bringing a variability into the signal, which is a kind of offset variability. I don't think this is the way they're intending to use the sensor. But that offset variability is causing them concerns about essentially the accuracy of the sensor, and I'll address that. I think you're testing it in a way that you're not intending to use it, so I'll address that. You do already have enough resolution for 0.5 millimolar resolution, but I got a strong suspicion that the way you're testing, you're bringing in a variable that wouldn't actually be there if you were testing in the way that you're intending to use them. And we do sell a chloride resilient cocktail, and I will link to that at the end. We do have 3 upcoming webinars, one on commercialization, one in the morning, one in the afternoon. I'll put a link here. All our webinars are basically repeated every month. So even if you're watching this 2 years later, you will find that these links will take you to the most recent webinars or most upcoming webinars. We are doing one on wearables on the 8th of May, one in the morning, one in the afternoon. We do the 2 just so that you've got a choice in terms of your time zone. And then we're doing one specifically for academia, one in the morning, one in the afternoon. Again, any links. I'll jump into the actual questions now. Question number 1 is really, they've got different solutions. The sensor is actually showing fairly good linearity in both solutions, but there's actually a big offset variability. That offset variability is causing them concern about accuracy. But I actually honestly think that offset is due to the way you're testing, and you're not actually testing, I think, in the way that you're actually going to end up using these sensors. You probably already have a resolution able to resolve 0.5 millimolar, and yes, we do the cocktail mixture. So this is your data. I was analyzing, my graphs are a little bit shoddy. I was analyzing this on a moving train, so I did what I could on the train. So you've tested, let's say there are 6 data points here, 3 of them in one solution, 3 of them in another solution. So this is 2 millimolar in a ZP potassium test solution, you get a signal. 4 millimolar ZP potassium test solution, you get a signal. And an 8 millimolar ZP potassium test solution, you get a signal, which is good. And then you go to a third-party solution and you test a 2 millimolar, 4 millimolar, and 8 millimolar, and again you get a signal. So I put them side by side here. You kind of get a similar trend in both solutions. This is the ZP test solution, and this is that third-party test solution. You get a similar trend in both solutions. You know that the signal changes proportionally to concentration, but it's actually the offset between the two that's giving you a concern. I'll mention in a minute that if you were testing the same concentration of potassium in urine versus sweat versus saliva versus blood as an extreme, you would get a different offset every time. So these sensors are sensitive, or at least the offset is sensitive to the solution that you're actually using. I'll dig into that a little bit deeper. So you've got three sets of data here, a data set of 3 here. And it's really the offset between the two that's most concerning. But I'd actually this is called the matrix effect. I think the matrix effect is a lazy way of people saying we're not really sure what's going on here, but it's a real, let's say, phenomenon. It's quite well understood in, let's say, the world of biosensor development, that in the end you have to kind of use a solution. You have to, going from solution to solution, biosensors won't necessarily give you the same sensitivity and the same offset. So you've kind of essentially discovered that in the work that you've done. And when you think about it, it would actually be unreasonable to think that the sensor would work the same way in saliva as it would in sweat. I think once you say that, yeah, you would think, okay, well, why would they? There's quite a difference in those solutions. Now, the difference in the solutions is probably more subtle between a ZP test solution and this third-party solution, but there's still differences, and offset is a very sensitive parameter. The way you're testing these solutions, you're putting them on, taking them off, putting them on, and taking them off. We've obviously got very nice data here, but we tend to sort of test in this regime where we'll actually be flowing over the sensor. So when you see our sort of nice looking data, it's because we're actually flowing over the top of our sensors. I think we're testing in the way that you would potentially be testing. You're testing in a way that you're not going to be using these sensors. Like, if you're doing sweat analysis, the user's not pipetting on, pipetting off, pipetting on, pipetting off. Pipetting on, pipetting off is a good way of kind of making sure everything's working okay. But in the end, don't judge the sensors based on that experiment. You'd have to probably judge the sensors based on flow experiments. So test and use the lab, at least judge them and characterize them in a manner that you intend to actually use them in the field. So that would be one of my comments here. I think that's, once you get rid of that kind of variability due to offset, and that offset is due to the way that you're pipetting on and pipetting off, then you may feel more comfortable about the precision, or sorry, I should say the accuracy of these sensors. This is a flow cell that we use. If you've got an instrument from ZP and it hasn't got EIS capability, then it's probably got what they call a 4-pin connector on the back. So you would need the flow sensor with this 4-pin connector. If you've got EIS capability on the instrument, then it's probably got a 5-pin connector on the back of it, and therefore you would need that one. And most of our sensors, biosensors, are 7mm, so you would use this. Again, I put a link here. You really are probably intending to actually do sweat analysis. So when I bring this up, because that's a very different configuration to the one where you're pipetting on and pipetting off. Pipetting on and pipetting off will bring you to a certain point, but each time you pipette on and pipette off, you are introducing a new offset, and that's that offset that's kind of clouding your consideration of the actual sensor. It's probably worth saying that when you're developing technology like this, you've got your technology readiness levels 1 to 9. So you're doing basic principles, you've done technology concept, you do proof of principle, you validate it in the lab, you validate it then in the environment, and then you start doing demonstrators, system prototypes, qualification, and system deployed. I'll bring this up, I'll zoom in a minute, but this is the Abbott Freestyle Libre 2. Obviously it has come up its 1 to 9 TRL levels, but in doing that they actually spent over $1 billion getting to that point. So the spend versus technology readiness level can be quite high. So at the moment you've done your basic principles, you've done your technology concept, you've done your proof of concept, you've done your validation in the lab, but just understand that some of the aims that you're giving yourself require a lot of funding, and I'll talk about that in the history of wearable biosensors in a bit. One of your concerns is about resolution. I think you can already resolve plus or minus 0.5 millimolar. The reason you think you can't is because you test by pipetting on and pipetting off, and every time you pipette on and pipette off, you have a signal plus or minus an offset variable, and that offset variable is what's clouding your resolution and also concerning you on accuracy. But if you actually look at our data here, this is on our website, there will be links underneath the video. You can see that we go from 4 to 5, 5 to 6, 6 to 7, 7 to 8. I bring these lines in just to show you that the signal is actually quite big and well resolved, and actually you can easily see that we could have resolved 7.5 between 5.5 and 6. We could have easily resolved it. So I think your concern is actually about your testing leads to an offset variability. That offset variability means you think you've got poor resolution. The poor resolution makes you think then you have poor accuracy, but it's really just the way the sensor's being tested. So you put a solution on there, you get a signal equals a value plus an offset. You put the same solution back on, you get a value plus a new offset. You put the solution on, you get a value plus a new offset. And if you're wondering, well, that's not very good, I would just say look at every pH sensor in the lab. They're all, most pH sensors are ion selective electrodes, and they've all got a set of calibration solutions next to them, because this offset variability It may not be intrinsically understood by the people manufacturing these pH sensors, but this is why they've actually got these calibration solutions there. We do sell a chloride resilient cocktail. Here it is, and here's a link to it as well. Just some lessons from history with this slide here. At ZP, we do a lot of wearable sensors and implantable sensors. We work on transdermal sensors like this. We do work on microneedles that look like this. I've got a few of those in front of me here, and I'll show them in a minute. You're working on sweat and sweat patches, so we have done some work on that, and we also work on implanted sensors as well. We have a package that gets implanted into marine animals. And I'm just going to change screens just for a second. So the reason I bring this up then is because I did mention that earlier on I was kind of saying, you know, that there's a point at which the amount of goodness you can get out of these sensors is going to plateau, because in fact you can't get the funding necessary to do this. So this is the Abbott Freestyle Libre 2. You know, it shows you all the good features of a wearable sensor. It's small, it's got a battery in there, it's got wireless. You know, it can be, it's accurate enough to be able to measure diabetics and control their diabetes. They've even just introduced this, I think at the NHS for the National Health Service in the UK. They've introduced something called the artificial pancreas, where sensors like this control insulin pumps. But Abbott, I would suggest, have spent over $1 billion to get to this point. So you've got to be sort of reasonable in what technology readiness level you can achieve on academic budgets. And in fact, you may need to do spin out companies and raise. And when I say raise now, let me go to the slightly different one. This is a wearable microneedle technology that ZP owns all the patents on. There's 50 patents behind it. That's easily had $20 million spent on it. It doesn't look much for $20 million, but it's probably worth knowing that this is what it kind of essentially takes. If I was to support that claim, that comment, I'd also say there's a company called BioLink in San Diego. About 4 years ago, they raised 100 million. Just in the last 2 weeks, they raised 50 million. So just understand that wearable biosensors are quite tough, and there's only a certain technology readiness level you can actually achieve in a lab, in an academic program, and actually there's a point at which they actually have to come out and become real companies that can raise the kind of money it really requires. I suppose one of the things I should say as well is that when this CGM first came to market, they were actually doing in-field calibration. So they didn't come to market with a calibration-free device. They were actually requiring people to prick their fingers, test a drop of blood, and then tell the software what the blood glucose was, so that the software could correct the signal. So I suppose a lot of this conversation is that, we would like calibration-free potassium sensors and sodium sensors in order to measure something in sweat. I would say for years, these CGMs, which is kind of leading this market, were actually not calibration-free, and they probably spent hundreds of millions actually getting rid of calibration. So be careful with your expectations. So question number one, you have a difference in signal from between two different solutions. It's not unexpected. You've found it, and we see it all the time. Your concern about calibration is, I think, in part because you're testing in the way that you're not otherwise expected to use these sensors. You do already have better resolution than 0.5 millimolar. If you maybe started testing in the way that you intend to use them, which is flowing, then you may find you can convince yourself, and we do have a chloride resilient cocktail that's available on the website. So I want to say thank you very much. Like I said, I recorded this because I seem to be suffering a terrible bandwidth issue this morning, but otherwise, if you've got any questions, don't hesitate to reach out to us. Okay, thanks very much.